The Pacific Northwest Building Resilience Coalition is a gathering of organizations primarily in the cement, concrete, and masonry industries committed to furthering the planning, development, and construction of buildings and associated infrastructure better able to recover from and adapt to the growing impacts of an ever-changing urban and physical environment. Hello, my name's Brent Taylor. I'm going to be speaking with you today on behalf of the Pacific Northwest Building Resilience Coalition. I'm going to talk today about carbon sequestration in wood building products. But before we dive into this story, I'd like to briefly explain why this is an important topic. Why are we here talking about carbon sequestration in wood building products today? Well, the built environment in Canada, which is the construction and operation of buildings, is responsible for more greenhouse gas emissions than any other sector except for the oil and gas industry. This means that policies to mitigate the impacts of climate change must include a comprehensive plan to minimize the carbon footprint of the built environment. Increasingly, wood-based building products are being promoted as the green alternatives to concrete and steel. And the argument is that while concrete or steel create carbon emissions during their manufacture, wood products actually sequester atmospheric carbon. On closer inspection, however, the climate benefits of wood products are severely overstated. Before we cover the wood product's life cycle, I'm going to introduce the concept of carbon neutrality in carbon accounting. Emissions resulting from burning biomass or biofuel are called biogenic emissions because they're biological in origin. Now, carbon neutrality is the idea that when biomass is burned for energy, or the carbon from biomass is released into the atmosphere in some other way, the emissions are not counted towards the carbon footprint of the product or process. Currently, all biogenic emissions are considered 100% carbon neutral. They don't appear in final emissions figures, for example, in environmental product declarations. The rationale is that these emissions represent only the carbon that was initially absorbed by the plants or trees while they were growing, and that they'll be reabsorbed by new growth later on. This accounting standard gives the wood product sector a major advantage in carbon accounting, since a large portion of emissions in this sector are biogenic in origin. Now, one problem with this concept, however, is timing. Emissions are immediate. Their greenhouse effects begin immediately, but it takes decades, or in some cases over a century, for them to be reabsorbed by new growth. In most cases, per unit of energy produced, wood-based biofuels actually emit more carbon dioxide than fossil fuels. For example, substituting wood pellets for coal-based energy actually increases emissions for up to 50 years before absorption from new growth would start to balance out the deficit. From a land use perspective, this accounting framework incentivizes the logging of forest land rather than the growth of forest land. Now, while the first-generation answer to the question of biofuels was that they were all 100% carbon neutral, there's a growing realization that this is not actually the case. Our current accounting rules for carbon neutrality were based more on assumptions than good evidence. And researchers are starting to conclude that these early assumptions were not completely accurate. For instance, a couple of years ago, the Science Advisory Board for the US EPA concluded that carbon neutrality can no longer be assumed for all biofuels. So our story of carbon sequestration starts in the forest. Forests are some of the Earth's most valuable carbon sinks. They're sometimes referred to as the lungs of our planet. Sequestration studies tend to assume that wood will always be harvested sustainably. Unfortunately, from a carbon management perspective, not all forests are sustainably managed. In fact, what constitutes a sustainably managed forest is itself subject to considerable debate. The old-growth forests of the Pacific Northwest are some of the most productive carbon sinks on our planet. These old-growth forests can be thought of as vast reserves of carbon capital. And we tend to think of wood as a renewable resource because trees grow back, but old-growth forests are not a renewable resource by any reasonable definition. If you want to renew the carbon stock of a harvested 200-year-old tree, you simply need to wait 200 years. One of the premises of sequestering carbon in wood building products is the idea that mature trees are less valuable than young ones. and it's argued that they don't grow as fast or absorb carbon at as high a rate. Unfortunately, there's just not good evidence that this viewpoint is viable. There's good research that shows that even very mature stands, centuries old, continue to act as net sinks of carbon. As a general rule, the older a forest, the more carbon it stores. Rotation lengths, which are the number of years between harvests, are sometimes as short as 25 or 30 years here in the Pacific Northwest. These are highly economical, but they have minimal value from a carbon management perspective. So there's a disconnect between the rotation lengths that are good for carbon management and rotation lengths that are economically preferred. In the forest ecosystem, the portion of trees that have economic value accounts for only a small fraction of total ecosystem carbon. In fact, about half of the carbon in the forest is stored in the soil. What this means is that to properly account for the impact of transferring carbon from the forest to the built environment, a much more comprehensive view of forest carbon is needed. Most studies on carbon sequestration in wood products omit the disruptive effects of logging on the soil carbon pool. And this is despite current evidence that logging reduces the carbon content of these soils. During a harvest, only a portion of the tree is removed from the forest for processing, but a significant portion of the tree's biomass is not merchantable, and this portion is either left in the forest to decompose or is burned. This represents large and immediate emissions that are not always accounted for. I mentioned a moment ago that old-growth forests play a uniquely important role in sequestering carbon. And we can see here the rate of recovery or reabsorption of atmospheric carbon after an old-growth forest has been logged. After 50 years of regrowth, only 38% of the carbon stored in the primary forest will be reabsorbed. After 75 years, 44% of this carbon is reabsorbed. And even after 100 years of regrowth, the secondary forest has still only absorbed a little more than half of the carbon that was once sequestered by the primary forest. This loss of terrestrial carbon to the atmosphere is a carbon debt that can take centuries to repay. At the primary manufacturing stage, about 40 to 50% of large roundwood logs are converted to lumber. The remaining 50 to 60%, called mill residues, are burned for energy to power the mill or sometimes sold to pulp and paper plants for use in products with little to no long-term carbon storage value. These emissions from wood waste and wood fuel are deemed carbon neutral and therefore omitted from the final emissions footprint of these products. This chart breaks down emissions from large facilities emitters in Washington between fossil fuel and biogenic sources. Now, as you can see, virtually all the emissions from Washington mills come from burning wood-based fuel, about 96%. These emissions that are omitted from final figures because they're considered carbon neutral are equivalent to burning nearly 1.3 billion pounds of coal based on the EPA's greenhouse gas equivalencies calculator. Now, the goal of transferring forest carbon to building products is to reduce the carbon footprint of the built environment. But this is a much broader task than carbon accounting for specific building materials. The energy and emissions associated with all the processes and materials from their source to the completed construction of a building are called the initial embodied energy of a structure. And initial embodied energy accounts for somewhere between 10 to 20% of a building's lifetime emissions. Given that operating energy accounts for 80 to 90% of a building's lifetime emissions, when we talk about building with wood, we're talking about materials selection, and there are a lot of factors to consider in this process. For instance, cost, durability, acoustics, thermal value, fire performance, moisture resistance, adaptability, and others are all factors to consider. Therefore, every material has unique benefits and drawbacks, and every material has a role to play in building better buildings. The factors that primarily influence lifetime emissions are design, operating efficiency, location and orientation, the electricity source for the building, the climate, the heating and cooling requirements, cumulative repairs and maintenance over the decades of service, and the longevity of the building and its components. The initial embodied energy is a small part of a much bigger picture. In order to get serious about reducing the carbon footprint of the built environment, our resources and efforts are much spent on building better buildings. Now, the last stage in the wood product's life cycle is disposal, and there are a variety of disposal options. The most beneficial from a climate perspective is recycling or reuse. Wood products can also be burned as a waste disposal option, sometimes to generate energy. And the third option is burial in a landfill, and herein lies a problem. Under anaerobic conditions, wood and other organics are subject to decomposition by methane-producing bacteria. In this process, the carbon in the wood is converted to approximately equal parts carbon dioxide and methane gas. Methane has a 100-year global warming potential 28 to 34 times that of carbon dioxide. And rising methane emissions from solid waste disposal sites are a serious global concern. Unfortunately, the magnitude of methane production from wood products in landfills is not well understood. There's a very wide range of estimates in both the laboratory models and the field data on this question. So the results of sequestration studies are typically influenced by assumptions that need to be made about landfill emissions because good data is unfortunately not available. To quote the authors of one study, estimating landfill methane emissions is fraught with uncertainty. In closing, this flowchart is going to help us follow the carbon through the wood product's life cycle and summarize the key takeaways. At each step in the process, wood products are responsible for emissions even if they're not always accounted for. First, a significant amount of the carbon that's stored in the initial living tree has little to no economic value. These parts of the tree are left to decompose or are burned in the process. As a ballpark figure, and this will vary somewhat from site to site, roughly half of the carbon in the initial living tree is lost at the point of harvest. Next, during the manufacturing process, as a general figure, about half of the carbon in the harvested timber ends up in short-lived products with little to no long-term carbon storage value, and about half ends up in long-lived building products. In the final analysis, a number of researchers have tracked the flow of carbon from forest to finished product, and this research shows that about 15 to 30% of the carbon that was initially stored in the living tree ends up in long-lived building products. The transfer of carbon from the forest ecosystem to the built environment is just not very efficient, and this process causes carbon emissions from a number of other carbon pools that aren't always accounted for. There's an irreversible loss of old-growth carbon capital. There are carbon emissions from the soil carbon pool caused by logging. There's the potential to see a rise in real emissions from the use of wood-based biofuels. And finally, there is a vast uncertainty in the final methane production from these products in landfills. So at the end of the day, what we can safely say when we talk about carbon sequestration is that living trees sequester carbon, and wood-based building products are the result of an industrial process that emits carbon. A more realistic and comprehensive approach to greening the built environment is one that's less concerned with material substitution and rather one that emphasizes building more resilient and energy-efficient buildings. For more information, please visit www.buildingresiliencecoalition.org.